check that we're good on YouTube as well and see if it's working. Because I'm worried it's not working. Is it working? Oh yeah, I think it's... Hold on. Is it working? It says waiting still. Why does it say that, Jaden? um... Because we're live on Twitch, I'm pretty positive. Are we
Cool.
live on YouTube, though? That is the question.
Alive on Twitch. I see us. You're so cool. I do see us
Yeah,
live on
it's working. Cool. Yeah, we're
YouTube.
good. Okay.
Yeah. Awesome.
Well, welcome, everybody, to our lovely live stream tonight. Tonight,
Hey, kid.
we are going to be doing...
How are you doing?
What, Jane? I'm doing good. How are you doing?
I'm doing
Oh,
good
wait, dude,
also.
you're going to be echoey. I got to do something real quick here because, I was waiting for you and I forgot. Got to put on the headphones.
Oh, good idea. Good idea. Alright. So you have a good day, Kip?
Yeah, dude.
And everyone else out there? You guys having a good day?
Yeah, man. How's your day been?
Been good. Nothing too crazy has happened, but it's good.
That's good, dude.
Yeah. So, Kip, what are we going to do today?
Dude, Jaden, so today we're going... I'm glad it's been a groovy day. Today we're going to be using what we've learned thus far in our class.
Okay.
And we're going to use that to solve some real world type problems. So we'll definitely review things as we go as well. So it's like if this is your first time watching, it shouldn't be too difficult, but there's definitely going to be maybe a little bit of confusion. But that's okay because you can go back and watch this whole series and then watch this video.
Dude, maybe I need to watch.
Dude, maybe you do.
Our past videos.
Maybe you do.
We'll find
out. But yeah. So to start off, let's go ahead and move on to the first slide, which is our review from last week. Yeah. So we've got, what is energy? And this is the part where you guys start typing away. Brrr, energy is this, because I am so smart.
Energy is this.
What is it? Don't spoil. Don't spoil. No spoilers.
Oh. I'm just gonna say the two types that we kind of talked about last time: potential energy and kinetic energy.
Ooh.
And you can also type in the chat, what's the difference between those two?
Energy is this! Exclamation point. That's not very helpful.
What?
I'm confused.
It is this.
Like that, dude? You think?
Yeah. I like that's good.
Anyone got an idea on what potential energy is? Or... Oh, did you see that subscribe thing pop up in the bottom corner? Wow, that's so cool. Maybe people should go subscribe if they haven't already.
True.
Or follow us on Twitch as well. We be on Twitch and YouTube now because we are cool. All right, Jen. Well, I guess no one wants to answer. So, energy is energy.
Isn't it the amount of work put into something?
Yeah, exactly.
Isn't that like one way to describe it? You could also describe it using a lot of equations like mass times the speed of light squared, that sort of
Yeah.
thing. But who knows what that means,
Who
right?
knows?
We don't. Not
So
in
we
this
do have kinetic energy is kinetic is the energy being used. I think it's something along those lines. That's close. It's moving energy. So that's really close, but it's kinetic
That was
energy
good. That
is
was
like something that's in motion is going to have kinetic energy. And then potential energy, it's the stored up energy, right? It's potential. It's what it's capable of doing someday. It's got so much potential.
for example, a roller
Jaden.
coaster at the top of the hill.
Oh,
Whee!
I
Yeah.
thought, I was saying Jaden has so much potential. He's going to go so far.
You too.
Thanks,
Because
dude.
I'm sitting on this bench, and if I fall off, I'll be converting that potential energy into kinetic. And I'm also on the third floor. So if I were to fall down all those stairs, a lot of potential energy converting into the kinetic energy.
Yeah, there would be.
Yes.
Cool. Um, Alrighty. So should we start then, Jaden? Here's how I'm thinking we're gonna do this tonight. Okay, we're gonna switch back
Yeah.
and forth between the slides because the slides have the questions, and then we'll go to the
Uh-huh.
Jamboard, solve, and just kind of flip flop
Okay.
back and forth. Okay. Sound like a cool
Okay.
idea?
Yes, it does.
Cool, cool. But guys, tonight we really want you guys to be as involved as possible because we're going to do some cool stuff and we're going to be asking lots of questions because this kind of is like a whole review of everything we've learned thus far. So get ready to pay attention.
Get ready.
Get ready.
Kip and I want to do as least writing as we can. Like, we don't want to have to do all
Yeah,
this.
we want that chat blowing up.
Okay.
Okay. So, first question, Jaden, is we're going to be talking about skiing. So,
Cool.
I went skiing this last weekend, and my mom was actually asking me about derivatives while we were skiing. And so I was like, hey, look, we're
Wow.
on a
What cool
hill.
mom.
Yeah, because she was trying to figure them out, trying to remember what they were
Yeah.
because she had been watching.
Yeah.
And so I was like, hey, this is a perfect example because literally the slope of a hill is the derivative.
Yeah.
And I was like, wow. So I can just use the hill that we're on as an example.
That's really cool.
Cool, cool. So let's go switch on over to our Jamboard. And now that we're here, so I kind of spoiled it a little bit, and we're going to be using derivatives. All right. So Jaden, I'm going to make up a function that kind of looks somewhat like a hill. Okay.
Are you gonna make like a piecewise function where it's like steeper here,
I don't
and
know. We
there's like a little
can.
exponential? We
But
could, or
we'll just keep it simple and
okay,
say
good
that
idea.
it's just like a rounded mountaintop. Okay. So we're going to say that this equation is going to
Uh-huh.
be f of x equals, this is our function, back to remember our very first lesson when we talked about functions, equals negative x squared plus
Cool.
100.
100.
100.
Cool.
Cool. So,
Okay.
for any of you people out there that remember, Jane, what kind of shape is this gonna give us?
So it's gonna be an upside down U.
And what makes you know that it's upside down?
Because
Oh my goodness,
the
I forgot to
coefficient.
switch my Jamboard. Thanks for the reminder. There we go.
I'm using invisible
I'm a
ink.
spy.
Yeah.
Yeah.
Uh, I know that it is an upside down U because we have a negative coefficient to our variable with the highest degree. In this case, we only have one variable, which is the x, and that is the highest degree because there's no other x terms in there, and it's negative.
So we have a question here that says, hey, remind me what a derivative is, asking for a challenged friend, a math challenged friend. No, thank you for asking. A derivative is an instantaneous change in something, or it's the slope at a given point or a tangent line at a given point. And I'm just actually about to draw this out, so we'll be able to show you
We can show it
you a little bit more.
there.
But thank you for asking. Because so, anyways, this is going to be an upside down U, right? And then Jaden, we have this plus 100. So what does that mean?
That means I don't know what our units are going to be, but it's 100 units up from our 0 line.
Yeah. Should we just go 100 meters, or is that gonna be? That's a tall hill, but it's cool. I think it works.
I feel like
So
skiing slopes are that
yeah.
long.
So if I was to draw my graph, okay, boop, we'd get this upside down U. Here's 100 up here, and the top of the U is gonna be at that 100, right? So look, we get this hill that looks like this. Whoa, oh, that's bad. Let's try that again. Dude, there's our hill.
Whoa, how did you know that?
Dude, because we just talked about it. It's an upside.
Oh, we just talked about
yeah.
it. Okay.
Okay. So now that we've got that going, so what we can do from here is what this literally represents, this function, right, represents our mountain. So here's me up at the top skiing. Boop, boop, woohoo. Okay.
Okay.
And so I'm on top of this mountain and I could go off either way. Yeah, Jaden, pay attention.
What?
Okay, so
we can go up.
But let's say we're going to go off to the right, okay?
Okay.
And I start skiing down. So the question that we're asking is find the slope at a given point, right?
Okay.
Okay.
I like that.
So the slope.
What point?
When we're at 90. Oh wait, but we're going X direction, huh? So we got to do it. So we'll do. Okay, so that's a good thing to remind me and refresh me of what we're talking about here, right? So remember, we've got X and Y direction, right?
Right.
And so in this case, the up and down is the Y, okay? But this function of X is a function of the displacement going out. So what that means is essentially, I'm going to be going down at an angle, right? But as we follow this graph down, I'm going to be going further and further out as well, right? When you ski, you don't just drop straight down, you go further and further out. And so why don't we just put it at like 50 or something, okay? So when X equals 50, so when I'm like at this point, right, to figure that out, I'd come up and draw a line and be like, okay, when I'm right.
X equals 50, we're going to be well below our x-axis.
You're right, dude. Sorry. Okay, we'll go x equals. Here, we'll go x equals 10.
Like trying 1 through 10.
Maybe 5. Let's go 5. Sure.
Let's go
5. Okay, so we want to figure out what the slope is at that point, right? And so if we remember, a slope is a rise over run, but this mountain's changing. It's getting steeper and steeper. I didn't do a great job of drawing it, but as you get further down, it actually gets steeper and steeper. And so we want to figure out what the slope is at that point. Okay?
Okay.
So in order to do that, we have to take the derivative of that function. Okay? So we do f prime of x, right? The f prime, the prime means that little dash, and that means that it's the derivative, equals a negative 2 x. Jane, how did I get to that?
Whoa, well, you took the derivative. This is using like a power rule. So you bring the exponent down, whoop, whoop, multiply it by the coefficient, and then you subtract an exponent, whoop, just subtract 1. And then derivatives of constants are 0. So our 100 becomes a 0, right? Plus 0. We have a 2 minus 1 here. Bring down the 2, times it by the negative 1.
Cool, dude.
Does that make sense?
That makes sense.
To anyone watching?
That makes sense to me, but, you know.
Cool.
So, Jaden, what do we do from here? You take over, dude. Now it's your turn. You go.
Because we are finding the slope at a given point, now we just need to plug in our point. Boop. So it would be f prime of 5 equals negative 2 times 5. Boop. Boop. That equals negative 10.
Cool. Thanks, Jaden. So I would say that this has been solved. Would you agree with me?
Yes, we have found the slope at a given point.
And for all you guys wondering what that actually means, that means right now we have this negative 10, which is the same as negative 10 over 1. So that means for every 1 meter, we go in the horizontal direction, we're dropping 10 meters. But that's only at that point after we've gone out 5 meters, right? And you could see if we've gone out 6 meters, then we'd plug in 6 for x, and we'd get negative 12. So then you would be going, why do I need to know that while skiing? Ooh, that's a good question. We're going to get into that probably in the next question here. But this is a way you can calculate the slope at a given point. And what we'll get into in the next part of this question is that slope will actually determine how fast you're going to be going down the slope at that point. And so the idea being not as much about whether or not you're actually calculating these things while you're going down, but it's just showing this is how skiing works, right? This is why if you're on a less steep slope, why you're going to be going slower than if you're on a steeper slope. We're going to show that. But the idea being the first part is you need to know what the slope actually is at a given point. And so the steeper the angle, the steeper the slope, it's going to be a larger number. Smaller slope will be a smaller number. And you can find that slope from derivatives. Nice. So let's get going here to slide number 2, Jaden. Ooh, ew, white background. We want the black. So if we go to part number 2 of this question, right, for skiing, what is the acceleration of the skier at this point? Oh, I get you. It's just explaining my fun world and why it's fun. Exactly. And it's putting it into
Yes.
our fun world, me and Jaden's fun world.
Yeah.
Yeah. Cool. So, yeah, the next question here is what is the acceleration of the skier at this point? Cool, cool. So, let's move back to the Jamboard here and get moving. Do 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 do. Okay. So, we have our ew. We have our no.
What's going on,
Dude, I'm
dude?
just drawing back. Okay. So we have
Oh,
our U here, and I'm only drawing half a U. Okay. And we have our point
okay.
here, which.
Because we just went down that.
What?
Because we went down on that
Yeah.
side. Yeah. Makes sense.
So we got 5. Okay. And so that's this point here on the graph. And we found the slope to be. What did we find it to be? -10.
-10, yeah.
So if I was to say, like, let's zoom in here. Boop. Okay.
Whoa, you zoomed in so
Not
much.
yet. I'm going. Look, so at this point, okay, even though it's a curve, we could zoom in. And at that point, we're going to get
Right.
a triangle, right? And I'm going to draw this triangle, hopefully somewhat to scale. So, we get this triangle like that. This is a really steep slope.
That's
That's
okay.
okay. They're going to be going real fast, though. Okay.
Yeah, that's okay.
That's okay. Okay. I was worried about that part. I was gonna like shrink our parabola, make it so it took longer for it to drop fast, but oh well.
No, we're doing it all right.
Yeah.
We'll explain the problem.
Yeah. Okay. So we got our skier. Here I am going down the mountain right here, right? And this is zoomed in at that point, and I'm going down the hill. Woohoo! And I'm
Whee!
having so much fun. And then, but now I'm like, Jaden, this is a pretty steep hill. Why am I going so fast? So, if we remember, the force of gravity equals m times the acceleration of gravity.
Yep.
Okay? And if we were to
Okay.
draw the force on me going down, or from gravity pulling down, right, it would be pulling me like that. Okay? But there, all that force of gravity isn't going to be actually pulling me down, right? Because I'm on a slope. And so that slope
So,
is pushing back up perpendicular to the slope. And so only a percentage or a part of gravity is actually pulling me down the hill. And that's why when you're on the flat ground, you don't move anywhere. And the steeper the hill gets, the angle of that slope is getting closer and closer to that of gravity.
yes.
So, how do we figure this out? Well, we got a triangle, Jaden. You want to do some trigonometry with me?
Yeah, I do. What corner will have our
I
angle?
think this is the angle we want.
Okay, I was thinking that one too. Cool. Because we're trying to figure out, because we have a y direction and an x direction.
Right.
Right? That's what we're trying to do. Whew. Cool.
And we're trying to find, yeah, it's, because technically this, the downward angle is the hypotenuse, right? Our magnitude is this, and we're trying to find,
yeah,
this angle right here. And so we draw our triangle like this, make that a right angle somehow. And
yeah,
lo and behold, I don't know actually.
Yeah, I think we're good.
Okay. Yeah. Okay. So
Okay.
remember, this rise is going to be 10, right? And this is going to be 1. Technically, that's a negative 10.
Because our slope is negative 10. Whew.
Phew.
You. Okay.
Okay. So from there, we can use some trig and say the tangent of that angle, right, is going to be the tan of theta, which is what we're going to call that angle, is going to equal opposite over adjacent. So we get negative 10 over 1.
Then we need to do the inverse to find the angle.
Yep. Which I don't know what that is.
Cool. Let's do a calculator, you think?
I think that's a good idea.
So we,
Yeah.
yeah. It's of negative 10,
Yep.
right? Our angle is negative 84. Well, I guess if we just use positives, it would just be 84.3
Okay.
degrees.
84.3 degrees.
Yep.
Equals theta. Dude. Okay. And then from there, Jaden, because of our trig, we can say that the force that's pulling them down at that angle is going to be mg times sine of 84.3, and that's going to equal the force that's pulling them down. So that's going to equal ma, because we remember that mass times acceleration equals force. Okay, so
Right.
if we want to find the acceleration, we can go ahead and cancel these m's.
Woo! So you're saying the mass doesn't even matter in this?
I'm saying the mass doesn't even matter. Pretty crazy.
That is crazy.
Dude, I would even say that it's math magical.
I agree, yes.
So, anyways, so essentially,
Okay.
what is the sine of 84.3? It's got to be like 0.92 or something.
It's 0.499.
What? That's the sine of
Sine
84?
of 84.
Are you in radians?
0.3, yeah.
You got to be in radians, dude. Cuz the sine of 90 is 1. Something's not right there.
Okay, let me 84 point. Okay, yeah, it was doing radian. Okay. Yes, 9.995. This is a very crazy skier.
Yeah, dude. So we get G times 99 point what? Or 0.99?
995. Yeah, 0.995.
So, for any of you out there that are curious what this means, is this means that this skier is essentially at free fall at this point.
And it gets steeper,
Yeah.
okay?
And it only gets steeper from there. So, to answer the question, why do you need to know this while skiing? This helps you to know that you probably don't want to go skiing down this.
Yeah, I don't.
So that's how that works. And you just found out how fast you're going to be accelerating. And if you remember what acceleration is, it's how quickly your change in velocity is happening. So the higher acceleration, the faster you're speeding up. So yeah, there's that part of that. And that is now solved. All right, Jaden, should we keep going on to part 3?
Yes, we should.
Okay.
And part 3, what is that
Dude, I think
now?
you should
It
do
is.
parts 3 and 4. I'm feeling it.
Did you think? Okay, how much work does a chairlift need to do to move the person to the top of the hill? So that we just need to figure out the potential energy at the top of the hill, don't we?
Dude, I think you're onto something there.
Well, that's not bad, right?
No, not at all.
Okay, we are on slide 4, yes. So our potential energy, I'll just do a big P with little e there, potential energy. Remind me again, that is mgh.
Yep.
Cool. Well, we know what the height of the slope is.
Okay.
So let's plug in all of our numbers. And I guess this is different for each person, right? If the chairlift has to work differently for each person because everyone's going to weigh a little bit
Yeah.
different. Their mass is going to be different.
Yeah.
So let's just leave that as M right now.
Okay.
We know what G is.
We do.
9.8.
Okay.
We know the height of the mountain. 100. And now you can just plug in any M you want.
Yeah. And
you get how much work the chairlift needs to do. Isn't that right?
dude, I think that's right.
Yeah, I feel like it's so simple, but
it is.
There it
It
is.
is so simple. Jaden, do you why though? Why Jaden? Why is because the question is the work, right, that the chairlift needs to do.
Right.
But you just solve for potential energy. So
So
I'm confused. Did you
work,
actually solve this question?
do you remember our review question where we said the energy is the amount of work you put into something?
Oh yeah.
So the chairlift is doing all this work to get you up to the top. So it's giving you more and more potential energy as it goes up the hill. And once you're at the top, that's, I guess, your max potential energy that you're going to have for the ski lift.
So I can't just magically get to the top and have no work done to get there?
Not that I know of.
Dang. So
Yeah. So the machine is doing all this work to get you up there. And then you're just ready. You're ready to use all this potential energy as kinetic energy as you're almost skydiving.
wow. So Jaden, we can go ahead and say this one's solved then?
Yeah.
Dude,
So if you're interested, put your own mass in this equation
Not your weight, your
in
mass.
kilograms. Your mass, yes, in kilograms. You could do a little conversion with Google, put in your pounds, say, hey, convert me to kilograms, and then you can put that number in and see how much potential energy you would have at the top of this mountain or hill or whatever we're calling it.
Yeah. Cool.
Cool.
So now, Jaden, the next question was, do you remember?
How much work does friction need to do to have the skier stop at the bottom of the hill?
Ooh.
So, Kit, I'm just brainstorming real quick before I even write anything down.
Okay.
We just solved at the top of the hill, we have our potential energy, which is that equation we just wrote down, right?
Yeah.
So, depending on who is calculating this, it's going to be different for everybody for their work. And you just need friction to do all of the potential energy that you write. Am I thinking through this correctly?
I think so. So wait,
The,
let's let's think about it. So what you're claiming, Jaden, is that
uh-huh.
the potential energy,
Yeah.
which was supposedly the same as the amount of work that was done by the chairlift, is
Yeah.
also going to have to equal the amount of friction.
Yeah, if you're going to be stopping at the bottom of the hill.
Which hopefully you are.
You're going to be on like glue at the bottom of the hill to get you to stop. But yeah, that's what I'm saying. It's going to be like sandpaper into glue at the bottom of the hill. That's just how I'm visualizing this, so I would actually stop at the bottom.
Okay. Well, I agree. Okay. Should we like write it out
Okay.
mathematically then?
Yeah.
Cool. So should we like sum up our energies then?
Let's do that.
Okay. Do you want me to do
This
that?
is
Or do you want you to do this?
you can do it.
You sure, dude? Okay, then you're
Dude,
you're doing all the skydiving, but
all of it. Okay, that's gonna be.
okay.
But yeah, so we sum up all of our energies.
So the first thing we need a total energy, right? And so we have
Right.
E total.
Are you still on? Okay, that answers my question.
What?
Keep going.
Sorry.
I was gonna ask if you're on slide 4,
Yeah,
but
I'm gonna stay
yeah,
on
that answers.
slide 4. So we have E total, okay, and we want E total at the top of the hill and at the bottom of the hill. So we're gonna set two equations, okay, and at the top of the hill, before you start moving, you have no movement. So the only thing we're gonna have is potential energy, okay. So we're gonna say ET equals PE, okay. Then from there, at the bottom of the hill, because of conservation of energy,
Okay.
we have to have the same amount of energy, right? So E total
Okay.
is going to be the same E total. But at the bottom of the hill, we're going to say we have no potential energy, right? Because our height is now 0. So that PE isn't going to be there. But we're going to have a kinetic energy, maybe, right? And then we're going to have the friction force, right, is going to be an energy there's going to be work done by that. And because it's taken out of the system, we have to add it back in, right, Jaden? And so we're going to say plus F E. So that's the energy of the friction throughout this whole thing. So now we can go ahead and we can set these equal to each other, and we can say PE equals KE plus Fe. And then the next thing we need to do is we need to say, well, wait a second. Is there actually any kinetic energy? And if we're completely stopped at the bottom, and we remember that kinetic energy equals 1/2 mv squared, and so that velocity,
if we're stopped,
there's no kinetic energy, right? Because kinetic energy is the energy of movement. So we get that the potential energy must equal the friction energy.
Wow.
So that's how you can, so the amount of work that the chairlift lifts you up to the top with must all be expended by the time you get by the friction by the time you get to the bottom.
That's pretty cool.
That's pretty cool. Jane, question. Does it matter, say, let's say the slope isn't very steep. And so it's a really, you know, instead of dropping really steep, it's like this, but we eventually get to the bottom. Will it matter? Will this equation change at all if I'm going to stop at the bottom?
Nope.
Nope. What if?
Because we have to keep in mind with what we just wrote down, right? Our conservation of energy, our energies are still going to equal each other. So no matter how steep it is, it's going to always end with your potential energy equaling this friction energy.
What if, Jaden, the mountain went like this? Woo, 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 woo.
Still doesn't change anything.
What?
Yeah.
Dude, that's crazy.
Because conservation of energy. That's why that idea is so important.
Yeah.
It doesn't matter what, even if you're doing all these snake turns, doesn't matter.
When you get to the bottom, it's always the same result. And so you can take super complicated problems and make them super simple.
Even if it's straight up and down.
Yeah.
Same idea.
Same idea.
You'll just splat.
Hey, Jen, that sounds like a great segue into our next slide.
Whoa. Yeah, I agree.
But by the way, this one is totally solved. Just in case anyone's... Oh, dude, I have been on there the whole time and no one told me. That's bad news.
Haven't been on what?
This slide. I've been showing just the slide and no one cared to tell me.
I didn't even notice either. Jeez.
Whoops. Shows.
Well, anyways.
There
we go. We might as well have not written anything.
Yeah, but
there we go.
Okay.
So now we're on to the skydiving.
Ooh.
What's the average height of skydiving?
I don't know.
Just so we can get an equation. Or altitude that we're jumping out at. I mixed up my 10,000 feet, they say. Okay, so now everyone imagine you're with Kip and I, we're going on an adventure, we're skydiving today. And we get a really exciting thing because we get to neglect our air resistance in the X direction, so in the horizontal direction. So we're going to be slowing down in the Y direction, right, because we have a parachute. Yeah. But our X direction,
we're a bullet shape in the X direction, dude. We're a teardrop.
Yeah. So this is really exciting. And that's so we can keep our projectile motion ideas simple for our class. But our first question with this skydiving is, what is the potential energy of the skydiver at the point of drop? Okay, So that was pretty simple, right? Just like our potential energy with our skier, we just need to know the height. So let's go on over to slide number 5. Our potential energy equals mgh. And we said the height is about
1,000.
10,000.
That's feet, though.
Okay, so we'll just keep m. So
That was
what?
feet.
Yeah, that was feet. Let's not do feet and
Just
let's do
divide it like
meters.
by
So that
3.
we'll just call it 300
Yeah.
meters.
See, dude, that's a really high ski mountain.
Not 300,
Yeah.
3,000, sorry. I was like, wait a minute, that doesn't okay. And our gravity, that is our 9.8. And our height, we're saying 3,000 meters. Okay. So this is our potential energy. Let's say, what's like 65
Yeah.
kilograms, 70
65,
kilograms
70
about
is
for
good.
Okay, so let's just throw in 65 for our M. Just call it a human up there because it's one of us, Kip, that are jumping.
Yeah.
So this would be our potential energy. We would solve that. Let's, I guess, do that real quick so we get a number.
Jane, what are you gonna get, dude? What's it gonna be?
19,110.
Wow, that's a lot of somethings.
That's exciting. So what would our units be? We have
That's
kilograms.
joules.
Yes, so that equals 19,000, I said 110 joules. Whee! That's a lot of energy, Kip.
Yeah, it is.
What are you going to do with all that energy?
Dude, I'm gonna burn through it all in a parachute.
Convert it into kinetic energy?
Yeah.
Jumping off of there. Cool.
Cool.
Are there any questions on this potential energy idea? I feel like it's one of the simpler things that we are reviewing, covering through this lesson.
Yeah.
If there aren't any questions, then let's just move on to the next part.
Which is what, Jaden?
Where will the skydiver land in comparison to the drop point? And this is neglecting the air resistance in the horizontal direction.
Okay.
Okay.
Are we neglecting it in the Y direction too?
Dude, should we just say we're
Just someone's free falling? No, I think what we should do is we'll say after the chute opens, then they're at this velocity and the Y direction. I think that's
so they're at their
so we
like we're only doing the projectile until they do their parachute.
No, we got to do it in 2 different sections. So you have
Oh, you're saying we're okay.
Before and after the parachute.
Okay, let's do it. Okay. Do you know off the top of your head when people pull their chute?
Nope.
Let's look that up.
Somewhere probably between 3 and 5 seconds, dude.
3 and 5 seconds?
Yeah. Jen, I forgot to hit solved, I think.
About 760 meters, you pull the chute. Okay.
So we could first figure out how long they'd be falling before we needed to pull the chute.
Okay, that's a good idea.
Should we do that?
Yeah. That So let's do our 3,000 minus 760 because that's how long they're going to be falling.
Okay.
Whew, whew. Okay. Quick, Kip, what is that? 3,000 minus 760.
Dude, it's gonna be 240.
2,400.
Yeah, something like that.
Awesome. Okay.
Wait.
So this is the distance that we're falling in the y direction.
Yeah.
Okay. We don't even need our x direction right now, do we? I don't think
I
so.
don't think so.
Then that would equal which kinematic equation?
Well, we have D equals VI T plus 1/2 AT squared. I think that may be a
Yeah, because
beneficial.
we have VIT plus 1/2 AT squared. Our initial velocity would be 0,
Yeah.
right? Because we're jumping out of the plane. We haven't moved anywhere. We have an acceleration. And what is that acceleration, Kip?
9.8, Jaden.
And how do you know that?
Dude, because it's a constant that you just memorize.
Good answer. Good answer.
That's just the acceleration due
So
to
that
gravity,
is the
right?
acceleration due to gravity. Okay, now we just got to do a little bit of arithmetic. So what is 2,400 divided by 4
0.9.
what was that? 0.9.
No, let's just make it 5 and
Sorry.
call it good.
Okay, so let's call this 10 then. Yeah?
Yeah. Jaden, I still think we subtracted wrong, because didn't you say it was like 730? 40? 60?
Oh, yeah, we did. 200.
That was the leftover, so it's gonna be. I forgot to put the.
You know, I'm just so excited to put that extra 0 on there.
Yeah. So it's gonna be 2,240.
Yes.
What do you? What is?
Okay, that was, yes.
There.
So we're calling the acceleration 10, just to make it
I'm
simple.
sounding
Divide
lazy.
by
What does that mean?
5.
Oh, because I wanted to
What?
divide by 5? Because it just comes out nice and easy. And you see this all the time that they use 10 instead. We're already neglecting air resistance right now, so that's not going to be that accurate. I mean, it's pretty accurate
Okay.
still. Okay.
Yeah.
So
Especially when we're.
we get 10.
So we get 440?
What?
Is it 440?
Where are you getting 4?
440.
Oh, yeah.
448.
Yeah, dude. I think you're right. Yep.
448 equals t squared. Now we gotta take our square root. Square root. What is the square root of 448? 1.2.
What? What'd you say?
21.2.
Wow, dude, you can free fall for a long time.
Yeah, that's kind of fun.
So let's just go over what we
But
just. I'm gonna hit solve because that's pretty cool. And
yeah,
so
figure out
what does that mean though, Jaden? Right? Like we literally just calculated how long you can fall out of an airplane for before you need to pull in
before
your
pulling.
chute.
Yeah.
And so if you didn't have like an altimeter with you or anything, and you were just falling out of an airplane, you would know when you're supposed to pull your chute. You could just count.
Yeah.
And if you're super fast, you
Watch
could
the clock.
you could calculate this while you were falling and be like, "Oh, I probably should pull my chute now because I finished calculating it."
True. Or you might be too late.
Yeah, if you're like us and you
Like
can't,
we probably would have
yeah,
been
we would
too
have been too late. We can't do simple subtraction, so
late. Yes. Also notice in this we don't have any mass in there. So it doesn't matter who jumped out of that plane, you'll need to pull it around this time, no matter who you are.
yeah.
Okay.
So Jen, it's 9 o'clock
That's
right
it.
now. Do we want? I'm trying to decide how much more of this we want to do. We took a long longer on that ski problem than I thought.
Yeah, we kind of did, huh? I didn't even notice it
We were
was
just having
9
so much
already.
fun, dude, because it was so
Yeah.
mathematical.
Yeah, I don't know. We can stop
I mean,
there.
it depends. What do our loyal viewers want to tell us to do?
Yeah, we'll just wait until somebody types to see what they say.
We didn't even get even close to the superheroes.
We didn't. Maybe that will have to be
Sometime.
some other.
I mean, we
Yeah.
could teach physics through superheroes.
Ooh, that could be kind of
That could
cool.
be kind of cool. Keep going. We got to keep going.
Keep going. Okay, what are we going to keep going? Are we going to see how much more time we have once we pull the chute? But then we would need to do all the air resistance and
Well, we can. We can. we what we could do is, I mean, we could just look at what the
yeah.
terminal velocity of like a human with a chute is, and just use that as our VI at that point.
Okay. How do we figure that out, Kip?
Google.
Okay. I like this.
Superheroes are awesome, but we will not be going over them tonight, but another time, maybe. And while Jaden's looking this up, I'll talk briefly about what our plan is moving forward. Probably next week we will not be having our class, but instead we'll be preparing for a whole new curriculum where we're going to teach how the world works through different, subjects. So for example, we might do one on music, and we might do one on photography as ways to kind of show, right, like how sound works, or um how light works using photography, as well as we can do a similar class that we've been doing on superheroes. So it just, it's more of a fun, exciting way to learn a lot of the same principles that we've already taught, but things that people might be a little more entertained to learn about. Jane, did you find it yet?
No. I'm trying to figure out the terminal velocity of someone with a parachute, right?
Yeah.
Um, all I can find is the terminal velocity of a human body.
I think it's probably somewhere like around, I don't know.
Because, I mean, it's got to be.
It's got to be like
I don't know,
2.
less than. Yeah, I was going to say less than 10 for sure. Are we gonna do meters per second?
Yeah, dude, you gotta be in the meters per second.
Okay. Let's do. Yeah, let's just call it 2 then. I don't know.
I mean, you kind of thud
Just
kind of
because
hard,
we could.
so it might be
I mean,
close to 10. You probably experience close to 1G when you hit the ground.
yeah.
I don't know.
Should we say 10
Sure.
or 5 or 8? I don't know.
I don't know.
But are we? Once we hit that point, right? We pull our chute. We're just assuming we're already there.
Yeah, we're not gonna do any sort of. It's just gonna be like a
Okay.
piecewise. We're not gonna
Okay.
have some.
So that we fall for what was it? 760.
Yeah. Are you on a new slide now, dude?
So yeah, number 7.
Okay.
So 700. We're using the same uh, formula, but this time we have an initial velocity, which is we are saying 10.
Yeah. 2. 2.
10. 2.
I don't know. I don't know what meters per second. Like,
Let's do 10 meters per second. That would be.
I know it'd be really fast.
That'd still be like
It's probably like 20 miles an hour.
20
Yeah.
something. Let's do 5.
Okay.
Okay. T plus 1 half. We still have the same acceleration.
Yeah, we
Are we
do.
still going to use 10?
Jaden, do we have an acceleration at this point?
Oh, no.
Haha.
Tricky because we're at terminal.
Velocity.
Dude. We don't need that second portion.
Nope.
Dude, you're trying to trick me,
I didn't
kid.
do it, dude. You tricked yourself.
You're trying to trick me. I was trying to trick myself. Well, this makes it a lot easier, doesn't it?
Yeah, should we briefly explain why there's no acceleration?
Yeah, let's do
Because
that.
it's kind of the whole purpose of a parachute, right?
Yeah. So you're not accelerating anymore when you hit the
Yeah.
ground? Yeah. Well, terminal velocity means you're not speeding up anymore, right? Your velocity is no longer increasing. Yeah. It's self-explanatory when you dive into it.
Yeah.
Get it? Because we're skydiving.
I get it, dude. Yeah.
Yeah. So if our velocity is no longer increasing, that means we have no acceleration. I don't know what else to say
Just
about
like
that other than
the other, like at that point, there's an equal force on the parachute, pulling you up as the force of gravity pulling you down, and that's right why your acceleration is 0, because your sum of forces is 0 at that point. So
right.
Those things together is why you don't speed up, and so you can get rid of that whole second part of the equation. So there you go.
Okay. And then we divide by 5 to get our time. 152.
Sounds good to me.
12.
Wait, no.
20.
Wait. 5 goes in.
That's a long.
Oh yeah, 12. Yeah. Sounds good to me.
Is that? I don't know.
Yeah,
we could do a
wait,
little
152 though. That.
Yeah.
Cool. So that means that you're falling 2,000 feet.
Seconds.
Yeah, so you're falling 2,000 feet, or 2,000 something feet in 21 seconds. And then you're hitting
for total time. T total time. That would be 152 plus 21. Did we get 21 point? I guess I said 0.2. But yeah, that equals 173.2 seconds to go about 3,000 meters.
Wow. So this is now solved. And Jen, do we want to figure out how far in the x direction we would end up if we... Because it's pretty simple at this point.
Yeah, you want to take over?
Sure, dude. I'll take over. So, our displacement in the x direction is just going to be d equals vx t, right? And we found our t here. Boink. And I'm just going to say...
Wait,
what?
why do you have the acceleration or anything?
Because we're neglecting air resistance, so there's no force acting on this person.
Okay.
Okay. And we'll say the plane is moving at 100 miles an hour, which is like, what is that? 2 point, or is it 4 point, no. Is it 2.5? 2,500 meters per second? Is that? No. Wait. That's too much math.
100 miles per hour
is
2 meters per second. Is that what you're saying?
Yeah. Google it, dude.
Dude, that is 44.7 meters per second.
Okay. So that's pretty good. That means that when we did our math, about 5 meters per second, that's about 12, 13 miles an hour. So that's probably actually pretty spot on.
Yeah.
14.
11.2 miles an hour. That's pretty good. Yeah.
So we'll just say 44. Okay. So 44 equals our Vx, and we times that by 173.2. And that equals some number that Jaden knows.
Yeah, I do. 44 times 173.2.
Yeah.
That is calculating 7,620.8 meters.
So that means that you're gonna end up almost 8,000 meters away from where you took off, or where you got out of your got out of the plane. Now we know that we will not normally neglect air resistance, because when you skydive, you don't end up that far away.
Yeah, with neglecting air resistance, notice we're still traveling 44 meters per second when we're hitting the ground in the horizontal direction. So the same speed that we left the airplane. So that's why that would never actually happen.
You'd be dead real quick.
And that's why we have this follow-up question.
Quick, let's look at it.
So the two last questions. So we figured out where we would land, right? That was the almost 8,000 meters away. And the last two little questions. If we neglect air resistance in the horizontal direction, does the skydiver survive?
No.
Oh. Unless, thought-provoking, now suppose the skydiver had a driver traveling in the same direction as a skydiver when they're about to hit the ground. And they let's say it's a truck and you land in the bed of the truck. Woo!
Be pretty cool, dude.
Now do they survive?
Dude, now they survive. And the thing is, the truck can calculate and know exactly where they need to be at what time. So it's physically possible. Because they just did all that math. The truck driver is the one that just did all the math that we just did.
Yeah. Good thing they had 170 seconds.
Yeah, dude.
Cool.
Cool.
Yeah.
Here, dude. I'm gonna say we're solved because I never did. And we're gonna go ahead and finish for tonight. So thank you guys all for watching. Again, we will probably not be having a video next Tuesday, like we normally do, but we will still have our lesson or our tutoring session on Thursday. So if any of you guys know anyone,
Oh wait, yeah, I don't know if I'll be there
dude, where
Thursday.
are you gonna be, Jaden?
I got invited to dinner.
Oh.
I'm so popular. Just, no, my old employer invited us to dinner on Thursday.
Dang. Okay. Well, maybe not Thursday then, but we'll see.
But dude, if you get on,
I might get
you
on.
could still answer some cool questions, I bet.
Yeah. Cool, cool. All right. Well, thank you guys and have a good